Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So, good afternoon and welcome to the afternoon session, which is Practical Astro Semantics Workshop. This is actually the fifth gathering we'll have had, which is devoted to astronomy and semantics in astronomy. I'm going to talk for about 25 minutes on just exactly what semantics and semantics in astronomy is, and then Norman is going to talk about some stuff, and Sebastian's going to talk about some stuff, and Ashish will talk about some stuff, and then we'll have a discussion about some stuff, which is what semantics really is, isn't it? So let me start off by giving you a definition of astrosemantics. And essentially, astrosemantics is the branch of astronomy which deals with machine processable knowledge. And it's nothing more than that, or it's nothing less than that. And it does this through the use of a set of technologies which you can broadly call semantic technologies. A lot of this stuff traditionally came out of the AI community and has been adopted by various bits of the web and things like that. But there's been precious little application specifically in astronomy, and what we're trying to do is promote the usage of these tools, because in the era of big data, everyone focuses on big data and doesn't think about big information or big knowledge, which is what you get necessarily when you have big data. Now, you quite often see this pyramid or diagram where you have data going to information, going to knowledge, going to wisdom, and the statement is that normally you'll spend about 40% of your time grubbing around in the data, maybe 30% of the time working with information, and if you're lucky, 20% up in the knowledge layer, and then the final 10% of your time gaining wisdom. However, by using semantic technologies, you actually invert that. And you, as a carbon-based system, would be spending maybe 10% of your time down in the data layer and maybe 20% in the information, but you'd be spending the bulk of your time up here in the knowledge and wisdom part of it, doing good thinking, good science, making discoveries, instead of wondering about why is my data crap and what can I discover in it. The bulk of this stuff will be handled by semantic technologies or smart technologies. I think smart is the way to think about this sort of stuff. That we're not talking about making intelligent computers which are thinking. We're just talking about making knowledge machine processable, so that you can then apply first order logic and the sorts of things that computers are really good at, so that they can handle that sort of stuff in the same way that they already handle basic zeros and ones. Now, why do we want to do this? What are some of the things that making knowledge machine processable would be good for in astronomy? So let me go to NED, and I type in an NGC number, NGC 7377. This is what NGC 7377 looks like. And it comes up with a whole load of annotations. One of the annotations that NGC 7377 has is most unusual galaxy. This is the most unusual galaxy in NED, so it is tagged. The reason is because if you go back to the original source paper from the 1970s talking about this, someone said this is a most unusual galaxy, and someone has annotated that in a fashion. But that means there's been a judgment call on this. There's something about this object which makes it an unusual galaxy. So if you could take that as a tag, you might want to go to a system then and say, well, if this is such an unusual galaxy in the opinion of someone, I would like to find other objects like this, either by type. Okay, so I would go out and find more spirals or more ellipticals. hopefully that someone has tagged that up. But what happens if instead of using a tag such as E, someone has tagged it up as elliptical, using the word elliptical? Somehow my system needs to know that E, the concept of E in this particular tagging system and the concept of elliptical in a particular tagging system are equivalent. That there is a concept scheme being used, that there is some piece of domain knowledge which says that when I'm tagging, some people might use this particular tag or use this particular tag. That's a piece of smartness that you want to put into your application at a very low level. Now, I might want to do it by properties. I might want to say that actually I'm interested in things which have spiral arms. And someone may have said that this is a spiral galaxy, or that this is a galaxy of S-type. Somewhere there will be a definition in your smart system which says these are the set of properties that in my worldview I will define a spiral galaxy as having. It will have spiral arms, or it might have dust lanes. If I say it has dust lanes, then I can do a search for objects which have been tagged as having dust lanes, and my system will be smart enough to know that that falls inside my definition of what I consider to be a spiral galaxy. The word spiral doesn't appear anywhere in that tagging, conceivably. There could be an object just says, this has got dust lanes, and that's what it has. It doesn't mention spiral at all. But when I do my search to get the objects like that, it'll come back and say, this is a spiral galaxy because it's defined to have dust lanes. I could say, find me more objects which are at the particular distance of this object. Now, there might be objects out there which don't actually have a specific distance metric attached to them at the moment, but they may say that this is a spiral galaxy. In my knowledge system, I might have something which says spiral galaxies have a distance measure or can have a distance attached to them through something called the Tully-Fisher relationship. And the Tully-Fisher relationship requires there to be an H1 line width attached to it. So maybe I can go out and find galaxies or objects which have an H1 line width attached to them, and somewhere there is defined an algorithm to say you can use that to guess a distance or estimate a distance for that particular galaxy using this particular algorithm or this particular property. That's a broader set of what domain knowledge would be, but I can express that in a machine processable fashion so that my smart system could go out and give me a data set that's usable, or that present me with a set of data that I could then do. So this is not just by tagging, it's also by inference, that I've expressed my knowledge and my information in such a way that the system can be smart about it and do things on my behalf that I've already told it or given it the knowledge to do so. On a completely different note, in Second Life, various people have, there's a little thing called a Semantic Museum. And what people have done there is that they have put, in this particular case, it's about classical Greece. There's a display about classical Greece. And they have created pictures of various objects from classical Greece. And they put descriptions of those objects in such a fashion that there is knowledge about those objects and about their provenance and how it's all connected together, pieces of information, pieces of knowledge that are connected together in a machine processable fashion. And what happens when you go up to the object is that a description pops up about the object. It's saying that this is a procus and it comes from the classical period of Greece. It sort of tells you what this is, how this was characterized, and it tells you something about the object and where it is. Now, each of those little pieces of information in there does not necessarily reside in a single block of text in Second Life. It actually is probably stored at the level of individual pieces of information. But you can connect the pieces of knowledge together like we're familiar with in Wikipedia, linking it all together, and you can retrieve it because it's all related and tagged together. You can also, because you've encoded the information in such a way and said that what the structure is, you can do clever things about multilingual presentations and all this sort of thing. So the term that I use for this sort of approach is artificial docence. Now, where this might be useful is if you're doing a sort of smart EPO type thing. So here we have a curiosity picture showing stratification on Mars. And, there could be a piece of text saying that, planetary scientists believe the same geological processes that have shaped Earth, volcanism, tectonism, water, ice, and impacts are at work on Mars. And there could be links then to descriptions about that and to find further information, further knowledge about that, which would be useful if you're exploring this sort of thing. Think of it as a very smart Wikipedia. Or it could link through to, let's say we're interested in impacts, and then it would then bring up the amateur picture of the thing that collided with Jupiter this week and say, Jupiter is important in the context of impacts because, and someone has put a description in there. Now I know that Ray was claiming that he does a lot of Wikipedia entries. So stuff that he puts in could be drawn up and presented in a fashion through a knowledge-based framework. And it would be reuse of the information that he's put in, not necessarily in the context that he originally put in, but if the necessary metadata to make it useful or to describe it or to use it in place, it can be put together for doing this sort of smart docent EPO type approach. A third area in which sort of knowledge can be useful is we as a species have this sort of innate need to classify things. And this is Lorai's sort of conceptual taxonomy for essentially variable stars or variable objects. And wouldn't it be great if I was doing data mining or machine learning in some fashion, and I could incorporate this knowledge not as a pre-processing step or as a post-processing step, but as something that's actually used directly as part of the machine learning or the data mining that I'm doing. Two particular techniques that I've been playing around with is there's a way you can use self-organizing maps to include what's called an ontology, which is essentially just a representation of domain knowledge, so that you can get a metric between two different knowledge ideas. You can get a metric between things that are expressed in a taxonomy. And if you go to Ned has the NGC catalog in it, as you've seen, and it has this wonderful set of annotations, and you can express that in such a way that it's machine processable and get distances between a spiral galaxy and an elliptical galaxy in your concept scheme. And because you then have a quantitative measure, you can then do traditional data mining clustering techniques like the ontological SOM or like a self-organizing map. So you take the NGCs, you figure out broadly what their classes are, you get a self-organizing map based on the distances of the concepts on how those objects are tagged up, and then you can see how those sort of relate. Another technique is a sort of superclass of Bayesian networks, which Chiro talked about, and I think, are you talking about Bayesian nets as well, Chiro? Ashish?
No, I'm talking about networks and Bayesian networks.
Right, okay, so Ashish will talk more about networks. There's a thing called Markov logic networks, which are a way of combining statistical reasoning and first-order logical reasoning. Essentially what you can do is you can express your domain knowledge in the form of rules, but you can associate weights with those rules. So the rules are expressing knowledge, and you can attach weights to those, expressing your believability in that particular statement. So you could say that a supernova is associated with a nearby galaxy 80% of the time. And you could then use that as a classification system, and it will use first-order logic to infer things like what is the most likely statement I can say about a particular piece of information based on a body of knowledge that I've associated with it, or marginal probabilities and stuff like that. So those are just three sort of separate areas where having machine processable knowledge could potentially be very useful in astronomy. So the question is, how do we use these tools? Well, the basic rule is that there is, in machine processable knowledge, there is the sort of the lowest level, the quantum of knowledge, is something that's very simple. It's what's called a triple. You essentially have subject, predicate, object. And you reduce all your statements to that basic level, that very fundamental unit. And then you do all sorts of other things with it, and express it in your concept scheme, store it in databases, infer over it. But that's the basic level that we work at. And the World Wide Web have defined a whole set of standards related to knowledge representation. And the basic one is called Resource Description Framework, RDF. And you will hear talk, if you read more about semantics and semantic technologies, you'll hear more about what are called triples or RDF triples. And essentially what they're just this subject, predicate, object. Pluto is a planet. Actually, it's not true anymore. That's the other thing about knowledge. Knowledge evolves, and our knowledge changes. If you work in biomedics or the bioinformatics, you have a thing called the gene ontology. The gene ontology, which expresses the current body of knowledge about gene structures, changes about 10 times a day. It gets updated about 10 times a day. So they are very used to having techniques for dealing with this fluid body of knowledge, and we change these ideas, we reclassify stuff and whatever. So that is sort of a bonus you get as well. It's inherent in there. How do we build up bodies of knowledge? Well, one way of doing it is extracting knowledge from the literature, and you express it in angle brackets, and we've been very good at doing that in astronomy for at least 2,000 years. In time domain astronomy, we send out event notices expressing our knowledge of what we've seen in the sky. And it essentially answers the question of who, what, where, when, how, and why. But actually, literature, there's a lot of information in literature, there's a lot of knowledge in literature that it is worth exploring and trying to extract. So this brings us into text mining and trying to create concept schemes from the body of text. Now, there are two ways you can create a concept scheme. I can go and ask George what he believes the correct hierarchy or the correct classification scheme is for variable objects. And I can then go and ask Bob, and they will have probably, let's hope, 80% agreement, but they may disagree over certain things. And I may ask someone else. Everyone will have their own version of what a concept scheme is and how you would classify certain things, or how things might be related, depending on what your domain knowledge is. That doesn't matter in semantics, because there's this whole thing about resolving different people's ideas to form consensus opinions and kind of hierarchies and how to map them. But going to the literature, where there is maybe a more established corpus of knowledge and a representation, is a good idea. So one of the things we've been playing around with is another way in which in time domain you can send event notifications around are things called astronomers' telegrams. These are natural language. So instead of trying to put it into a force structure like we have maybe with the angle bracket way, with the ATELs you have someone has written some sentences. Now the hope is that these are scientifically rich sentences, but there may be things that are very useful in there which might allow us to gather snippets of knowledge together that are relevant for a particular class of astronomical object. So I've had students over the last 2 summers who've been working on this and trying to hierarchically cluster vector representations of text that they extracted from ATELs, and there is some interesting clustering going on that would maybe allow us to create a concept scheme for that particular subdomain. This is another thing. You don't need to create one huge overarching body of knowledge. This is astronomy and that's what you've got to use. You can deal with the very small subdomain of which you are expert and just work with that, and maybe use someone else's representation of which they are also expert, and then join the two together quite easily. ADS Labs is a potentially very rich corpus of material to mine and create these sort of concept schemes, and I think there is work that has been done or is being done in these sort of areas.
Next talk, I think.
Okay. There was David Hogg has been putting ideas up on his ideas blog last month, and one of them was about creating a paragraph level index for archive. Wouldn't this be a great way of identifying astronomical knowledge, and as he says, also identifying who wrote which paragraph in a paper. And then there are things like the NED annotations. They are somewhat free form, but you can create a concept scheme from those, as I've sort of half done, and present that and say, this is the worldview as according to NED. Use it if you want. But those would be concept schemes from bodies of knowledge, bodies of data that we already have. How do you store this information? How do you store knowledge? Well, for a separate project, one thing that I have done recently is we had a corpus of information we had about 11,000 event notifications, and we wanted to see what the best way of representing the knowledge, the information stored in those was, and for retrieving it. And you see there are these things called triple stores, which, who talked about? Mark Stolzer was mentioning with the flash blades on Monday. And we have relational databases, we have things like NoSQL, non-relational databases, which are seen as one of the storage solutions for big data. Now, with LSST, we're going to be getting not 11,000 events, we're going to be getting about 10 million to 100 million events per night. That knowledge, that information needs to be stored somewhere in a very efficient way. So we were looking, doing a little toy experiment to see what we could do to store those. So we tried a traditional relational database with two different ways of organizing our information inside that. We tried MongoDB, which is, I think, what Galaxy or Zooniverse uses under the hood. Stardog, which is a commercial triple store, and Exist, which is a native XML database. VO event is an XML, it's an angle bracket representation. And so you just give it a very simple thing. In this case, find me all events which have, a parameter called event flux and a value less than 40. So there's my knowledge statement my knowledge query, find me everything with that in. And it turns out that the triple store is by far the fastest because it's the technologies are very fast at retrieving these sort of very the semantic triples. Which is essentially you break it down and then you're just doing matching. So I was quite surprised by that. I fully expected MySQL, the relational database, to win out, but this particular product did. We had hoped to have the creator of this particular product here this afternoon, but he had to call off at the last minute. But there are these specific technologies for storing very large amounts of knowledge data out there, which will scale very nicely, I suspect. Finally, there are these different ways of codifying knowledge, which I've alluded to. We start off with controlled vocabularies, and the semantics working group of the IVOA is very much into trying to collect these and provide advice on how to do these. So we start off with controlled vocabularies. The theory working group has produced one of these for marking up astronomical theories. There are taxonomies like the General Catalogue of Variable Stars defining how a hierarchy of variable stars. There are Thesauri, which Norman's going to be talking about in a few minutes. And then we have these things called full-blown ontologies. CDS uses one of these for doing a lot of stuff. And I've talked about the concept schemes that I've been working on, data mining, and there are a couple more out there. Something I finally came across yesterday, which I was very interested to see, is something which is putting all of these together, which is the SKA Information Intensive Framework, which has been developed by the IBM CTO and someone in New Zealand, which provides semantic services to manage data right across the board for ingesting, for classifying, for making inferences, to do transient detection, and for data retrieval. This uses one of the ontologies that the IVOA has defined. So I was very interested to see this. I'm trying to find out more information because there seems to be very little information about it. There seemed to have been a set of press announcements about it at the end of the last year. But clearly, SKA has got its ideas right about how to use knowledge and knowledge management systems in the heart of a big data system. So I'll.
SKA in the sense of square kilometer array.
Yes.
It is.
It is. Yes. It's the guy who proposed it is the chief technology officer at IBM, who's also in charge of some aspect of SKA project management. So I hadn't heard about it before I happened to see a random news story on it yesterday. I was quite surprised by it. And Ray says he knows nothing about it. Yeah, I know. I don't know if Joe might know more. Joe's not in the room. I'll ask him later. So that's where I'll end off. So if there are any questions or comments.
Hello, again. As Matthew mentioned, I'm going to talk about the history and future of broadly considered vocabularies in the context of the VO, which in this context often means within the IVOA, but not exclusively. So, that wasn't supposed to happen. I'm going to skip these slides because they are implied by the discussion we had in the last session. Close parenthesis. So, the core assertion here, the thing I want you to remember, is that there are multiple thesauri, and I'll come to definitions in a moment, already within astronomy. This is no longer arcane, even if it was originally, and this is all ready for deployment and for applications to build on it. This needs saying because this whole area, the vocabularies, thesauri, the semantic web, has appeared to be off-putting to people. And that's intelligible because a lot of the technologies involved are sufficiently far from the comfort zones of most people in the physical sciences. They were new to many computer scientists until 10 years ago. And they're sufficiently fiddly that they're a long route from reading the README of a download to producing something interesting and useful. So you needed to be sort of pre-convinced before it was worth that effort. But now I think there are enough applications or potential applications or fairly obvious next steps that is no longer the case. So that was true in the past, no longer now. Now, as Matthew mentioned, there are vocabularies, there are thesauri, there are ontologies. So some definitions are useful. So this section of the half hour is fairly pedagogical, and the pedagogy will be through stories. I don't expect you to read all that. You can read it in the PDF of the slides. You can, and I encourage you to do so, read it in the PDF of the slides afterwards. The main point is that there's a story here of someone starting off reading a paper and going from there to service, to data, to other things, including Wikipedia, and moving around through the possibilities of astronomical knowledge to make their work easier. Now that works, that doesn't work yet, but getting from where we are now to there is just a matter of code. There's the bare bones of that are already present, and things like the deep linking or the deep markup that deep tagging that Michael mentioned in passing in the last session would support this. The point is that one of the points that I'll come back to several times is that what supports this, doing that is easy for humans because the web works like it does. If you're reading a web page, you can follow a link. That link isn't restricted to going to another place on that page. It's not restricted to going to another page on that site. The link can go anywhere on the web. but only humans can read HTML pages. This depends on a machine-readable web, on machines able to do the same sort of service-to-service to source-to-source linking that humans have always been able to do with the web. I don't think there's much more to say there. This is very lightweight semantics. That word again. This is very lightweight stuff. At the more elaborate end of the range of possibilities, you can talk about ontologies. And I'll skip over this fairly swiftly. I just wish to assert or illustrate that there is a heavyweight end of the spectrum. What does this mean? That's an area in a deck and an R magnitude by some particular observer on a particular date. What can you conclude from that? Well, this is an optical measurement of a star. You know it's a star because it has an area in a deck. It's optical because there was an R-band measurement there. Now, Iseult there is an optical astronomer because she's taken an optical measurement. She was not at a radio observatory on that day. You can tell that because she was clearly at an optical observatory. And optical observatories and radio observatories are different things. And so you could ask, who was at an optical observatory in March, and you could never give an answer to that question. Or in other words, there are rules here. If it has an area in a deck, it's a celestial object. If it has a measurement in the optical, it's visible in the optical, and so on. Now, all of you are sitting there thinking, that's not true. I can think of counterexamples to that. And you are right. This is not absolute truth. It's a programming language. If you write a simulation, that what you're coding up is not absolute truth. It's enough of the truth to be usable for to get something done, to draw a conclusion. And so this is the sort of more elaborate programming with logic that reflects enough of a discipline that the machine doesn't understand what's happening, but it can act a little bit as if it did. And that's the fairly modest goal of things, even at this fairly heavyweight end of the spectrum. And I mentioned a spectrum. And a spectrum, this is a much PowerPointed picture. You can imagine a spectrum of these from very lightweight knowledge representation things at one end to very heavyweight knowledge representation things at the other end. Way over here are lists of terms. You've seen things like that. If you submitted a paper to one of the major astronomy journals, you have to add keywords to the paper. Now, those keywords have no structure, but you have to pick one or two of them. There's a controlled vocabulary. You can't just put in any keyword you like. You can do a little more than that. You can add structure to those keywords. You can say this is a narrower term than this one. The canonical example there is if you have a car, concept of a car. A steering wheel is a narrower concept. There's less covered by that concept. It does not follow that a steering wheel is a type of car. So the relationship is about finding things. It's not a subclass relationship. Going the other side of this red line, you can talk about more formal ISA relations. So you have the class of all cars and the class of red cars. And if you say something is a red car, then it is a deduction that it is a car. Nothing exotic there. That's a very lightweight bit of logical structure, but it's the very beginning of how you can imagine sort of classifications based on that sort of structure. And over on this side, you have much more elaborate, intricate types of the same sort of thing. But there's a sort of boundary of vocabularies and thesauri on this side and ontologies on this side. There's also a boundary of cost. Things on this side are easy and cheap. Things on this side are not easy and emphatically not cheap. And all of them are contestable. As Matthew said, this is not about having one grand ontology or thesaurus. So keep that in mind. I'm now going to go on to talk about various thesauri and vocabularies that already exist, just to show the range of things, and that are being developed further at present. One control vocabulary that many people know about is UCDs. Everyone knows about UCDs. And these have evolved over the course of years. Not hugely, but there are developments. The UCDs are barely structured. There is some structure sort of there, but it doesn't play a heavy role. The reason why UCDs are so important is because everyone recognizes them. And they have their authority from the fact that they were extracted, they were deduced, they were mined from the headings of the databases in the holdings of Thesauri. So these aren't just some words that some folk thought up that might be a nice idea. This is a collection of things that are actually measured in astronomy. So they're not intricate, but they are very well known. And things like that led on to work in 2009, where the IVOA declared, in a rather tentative declaration, that everyone should use SCOS. SCOS is a W3C standard for writing down simple knowledge organization systems. So it says these are the important features of a thesaurus: the idea of a narrow relationship, a broader relationship, a related relationship, and that's about it. So very lightweight. This document simply said, that's a good plan. If you're going to produce thesauri in astronomy, do that. And it mentioned, as examples, it showed SCOS versions of 4 existing thesauri, namely the journal's keyword list. So basically the list of keywords required by the journals with angle brackets around it. The UCDs, an outreach vocabulary called AVM, and the IAU's 1993 Thesaurus of All Astronomy, which it was an intricately constructed thesaurus, but which hasn't been updated in 20 years, and so is of limited use. And that, again, illustrates a point that I'll come back to, that it is useful to... these thesauri don't have to be complete, and they don't have to be new. They can be repurposed versions of existing things, and there's value in that. So, what does one of these look like? The concepts are named by URLs. You can describe broader narrow relationships. The concept is different from the labels that describe it. So the concept of absolute magnitude is not bound to the string absolute Heiligkeit in German, or absolute magnitude in English, or and so on. So the labels are a separate layer on top of the notion. And there's pointers to other related things. So nothing exotic or particularly arcane there. This is about lightweight semantics. Another, that's from the IAU's thesaurus. Another set of terms is Simbad's object types. Again, not hugely structured, but well understood and applied to a very large number of objects. These are effectively a lightweight ontology of astronomical objects. Sebastian can say more about that, I'm sure, if there are any questions at all. Also from CDS, and this time at the heavyweight end of the spectrum, is the ontology of astronomical object types, which really needs a snappier name. It's at that URL by these people. That version was finished in 2008 with some tweaks later. And I put this up to point, not because I have much more to say about this, but because I want to point to these notes describing it and the use cases for that, which I think are interesting. This has had a couple of applications. Matthew mentioned one. It has been used within CDS to do consistency checking of the attachment of labels to astronomical objects, to see if somehow something has been inconsistently labeled. So that, I say, is at the heavyweight end. One thing that's sort of missing from this talk is snappy demos. There are not. I said at the beginning, and I will say again at the end, that these things are much more mature than they were, and there are many more usable, ready-to-use things than there were in the past, but they're not quite there yet. So I don't have snappy astronomy-specific demos, but this general technology does work at scale, and the BBC's sports web pages are, I understand, essentially a semantic web application. There's a big triple store behind them. None of the pages are fixed. Now, of course, that works. This is just being used as a content management system, and this is not the only place that uses the content management system. But this content management system is firmly based on the technologies that I'm talking about here, and is obviously at a big scale. And I picked this particular screenshot because this is, although it's only the sport stuff that is covered by this application, it's flexible enough and it has enough links across the BBC that this is basically a news story from a non-sport news story that has enough of a sport angle that it's included in this, as one of the sport headlines, as it happens as today. So one of the things I've been saying again and again is about linking between vocabularies. There are multiple vocabularies and you can link between them. And this has been systematized in the notion of the linked data cloud, and I did not expect you to read that. The part of the point is it's too big to read. Each of these is a data store, some sort of data warehouse. I think these ones are publications of various types. These ones are community content. These ones are governmental ones. But the point is they link from one to the other. Each of these gives its information available. It gives out its information as RDF, as these angle brackets that I showed you in the illustration of the thesaurus, and makes links from one to another. This is just like the ordinary human readable web. But the point is this web of links to links to links to links, all going via Wikipedia, is mirrored here in a computer readable version of the web. In this case, going via DBpedia, which is a machine readable version of Wikipedia. So this is not a fringe technology anymore. That's the point I keep going back to. So, bigger projects. One is the grandly unified astronomy thesaurus. This has various people involved. I think the important thing here is the range of institutions involved in developing this. And the history of it is that it was, the history is implied by what I say, the slide after next. One interesting thing is the use cases. These are some of the use cases for ADS. I'll let you read them, but the point is that having this structure, machine readable and shareable, allows applications to be built on that foundation. The publishers have similar, distinct but similar use cases. There are different things they want to do with the same structure. And if they're doing things with the same structure, then it's very natural for these applications to go back and forth between the very commercial publishers and the community-oriented ADS and beyond. The goals for this are fairly specific. The background to this is that both the American Institute of Physics, AIP, and the Institute of Physics, IOP, in the UK, were generating large all-physics thesauri. And they have donated the astronomy portions of these to this project. So there are some incompatibilities. Both of those thesauri have in their lineage the IAU's 1993 thesaurus, but they've come by different routes. Productizing this is important because this mustn't end up being just a research project. This must end up with being a thing which is released and which can build long-term applications on. The maintenance process is important because it's necessary that there's not fall out of sync with astronomy as the IAU's thesaurus did. And so a mechanism for involving astronomers, not information scientists, but astronomers in the creation of it is important. And echoing what Matthew said in the last remark, this doesn't have to be complete. It's okay to have more than one thesaurus. The process, AAS, American Astronomical Society, will own this. IAU expects to bless it. The process is not terribly exciting, but the point is that there is one, which is yet to be sort of baked a bit and finalized. There's nothing more to say about that. Okay. Moving on, another cluster of thesauri are the VO theory vocabularies, which again Matthew previewed. These are the folk involved, folk at Paris Observatory in Meudon, and I've been involved a little bit, although it's the Meudon people who've been doing most of the work. Now, the motivation here is that the simulation data model within the IVOA is about finding simulation results. You can search for these, is the plan, by searching for the objects being simulated, by searching for the types of input parameters, by searching for the algorithms being used. And so you don't just want to just have free text searching for all of this. You want to be a little more structured. And so these need thesauri, plural, for these efforts. That's the site, votheory.obspm.fr. And there's 10 vocabularies being curated there. Some of these were pre-existing ones which were just tagged up and imported. Some were given more or less substantial editing work after being imported. Some were created on this site. Now, the back end of that is our commercial system called Pool Party, which is a rather expensive system, which we have a free license to use. But because this is using SCOS, we're not in hoc to that commercial supplier. If they disappeared or insisted on charging, then we just dump the SCOS files and go somewhere else. Such is the virtue of standards. I'm going to talk now about one of these in particular, one of the thesaurus for chemical species, because I was involved in elaborating that a little bit. It builds on the VAMDC, Virtual Atomic and Molecular Line Database C. I'm not sure what the C stands for. That's quite a large thesaurus of chemical species of astronomical interest. And here is a term from it. I put this up here just to illustrate what the thesaurus looks like. There's some URL which refers to this concept. This has the label, a couple of labels. This is water, the concept of water. It has preferred names, alternate names, and narrower concepts, which are the concept of heavy water and tritiated water are narrower concepts than this. I'll make that point next. Now, in this case, heavy water is a narrower concept than water. You find that in the same part of the shop, if you like, as the shop where we find water. Not very much of it, typically, but it is also the case that heavy water is water. It's a type of water, and that isn't captured here. That implication isn't present in what's up there. So the way that the solution to that was to write a parallel, to generate a parallel. That slide did just change, by the way. I draw a parallel ontology which does talk of subclassing, that heavy water is a type of water. And the other thing is that this very naturally can link to other sources of information. This is clicking on a link. Other source of information about water. CHEBI is chemical elements of biological interest, which is another elaborately and I think expensively curated source of machine-readable knowledge about chemistry. And so it is natural for this fairly homegrown bit of work to link into that and thus inherit the knowledge which other people are expensively creating for, in their ontology. So that linking and the machine-readable linking is like a broken record I'm coming back to again and again. So there are, just to make explicit the various lessons that I've been mentioning in passing through this last 20 minutes. A little bit of structure goes a long way. You don't have to have elaborate, logically intricate descriptions of the entire astronomical world in order to build something useful. A little bit of structure is enough. Most of the work involved in the various thesauri I've described here has been scripting work, just taking something which already exists, which possibly people believe in and use in one little part of the forest, and putting the right angle brackets around it and making it a standard and openly shareable and reusable thing. It's okay to have lots of them. There's no benefit really to having a monolithic thing here. A monolithic thesaurus has the virtue of consistency and some internal integrity, but it doesn't have many other benefits. And if you had a whole forest of these things, as long as they were linked together and not logically inconsistent with each other, everyone maintaining all those little bits of the tree can have their work useful. Thesauri don't do everything. Sometimes adding a companion and very lightweight ontology, which just expresses a few extra relationships, is necessary. And as I've said several times, this is all about machines being able to do what we do on the web anyway. Is move from source to source. So I'll start where I began. There are already multiple thesauri developed and deployed. This is no longer arcane. This is ready for applications to be built on top of it. So what are you waiting for? And I'll stop there. With plenty of time for questions.
Yes. Any questions for Norman?
So you showed this linked data stuff. Mm-hmm. Is there any astronomical data in there already?
No, none.
Okay.
Well, that's not strictly true. Any astronomical data that is in Wikipedia
Yes.
and is sufficiently marked up will be
real data from
real data.
So in that sense, each data is your main goal in this area to connect to the linked data web?
Where I know exactly how to put astronomical information on there. There's a lot of information in Simbad, for example, which is exactly the sort of information about astronomical objects, which could go onto that, perhaps not tomorrow, but it's only a matter of code. And no, that's not true. It's a matter of code and permission to use that data that way.
So to connect something there, you have to create an RTF database, right?
Not necessarily. You have to give the information out as RDF. Right. But you don't have to store it as RDF.
So in the case of the virtual observatory, would it be possible to connect the virtual observatory to the linked data web?
The linked data web isn't really about bulk data. RDF tends to be slightly uneasy. Well, it's not natural to pump vast quantities of numbers out that way. It's about concepts, about the sort of knowledge that you have after reading a Wikipedia page.
So one thing that we did experiment with at a previous semantic workshop a couple of years ago was putting an interface around Simbad for the information in there, or a subset thereof. And there are ways that you can put layers on top of relational databases, and then you just define the mapping into the RDF. You don't need to reconvert all your data already into it.
Yes.
And we sort of got some way with that. So that might be a way of doing something similar to that.
Yes. So the way that the proof of concept way that I had of showing a linked data version of Simbad was just with a layer which took the linked data API on this side and made the right sort of SQL queries and rewrote the results.
So, for example, I could easily imagine in a VO context browsing through these relationships and stepping from one to the other. But also some of the relationships could tie into data. For example, some of it might already be done at some level. I know, for example, Space Telescope shares with ADS the relationships between data sets and publications. And so that's a very natural sort of stepping off point in both directions,
yes.
Depending on maybe you discovered some data sets and you want to know what publications, and then you can go from there to other data sets and so on. And it's a very natural sort of way to expand the sort of scope of things that may be of interest to what you were browsing.
And this provides a language for doing that.
Exactly.
But this is glue. It's a pot of glue sitting there, ready to be used. And once you've done that for machines, it's just a matter of code to do it for human readable pages as well.
Okay, last question.
It assumes that we will produce these triple stores for output.
Last one from Arnie.
I didn't quite follow the context that you mentioned UCDs in.
Okay, I was using those as an example of a quite lightweight controlled vocabulary with some structure, but the structure isn't the important thing about it, which gains its authority from the fact that it is used by many people and that it was harvested from Thesauri rather than being the creation of someone's beautiful mind.
But they do have a useful role to play.
Well, it's very useful. In a way, the point that would be made there was that even something as lightweight as UCDs is the mere fact there's an agreement that use this string. Even that is enough to get lots of useful things done. So if you have more structure in the thesaurus, you can get even more things done. It's a sort of existence proof of function from any consensus.
Right, okay, thanks, Norman. So our next speaker is Sebastian Derriere, who's going to be talking about building a smart portal for astronomy.
Okay.
Thank you, Sebastian.
Thank you, Norman. Thank you, Matthew. So I could have made the title Improving the CDS Portal. Well, it's that this is more ambitious, and I hope
Already smart.
it's already a bit smart. So I will start because portal is maybe a fuzzy word. I took the official definition of the word portal in the Merriam-Webster dictionary, and so the first there are several meanings to portal, and the first one is a door, entrance, especially a grand door, imposing one. So that sounds good. I hope we can build a portal to astronomy or a unified portal for all CDS services. There are then other meanings. One has to do with church, and one with a tunnel. So I'm not sure we want to go that way. Or an entry point for diseases or pathogens in the body. That's not good. And the last one is quite modern. I think it's quite recent definition. It's a site serving as a guide or point of entry to the World Wide Web, and usually including a search engine or a collection of links to other sites arranged especially by topic. And maybe they had a hard time coming with this kind of definition. I don't know. It's still a bit fuzzy. You can go to the World Wide Web or do some searches or point to different things. And in fact, when we do portal, we have the same kind of problem. So my definition for an astronomy portal is a bit more restrictive. I see astronomy portal as a web interface or web application because it's more and more integrated somehow. Something that will allow to do some data discovery or service discovery, and maybe them doing some queries to the various data set or services. Then why not do some analysis, build some workflows, and so on. I will do more and more of this in your browser. And if you want to do complicated things, then you will need some kind of customizable interface where you can put modular widgets as you want, and these widgets will communicate with each other and maybe communicate with external applications. And we start to have some technologies which do all that. We've got very nice JavaScript frameworks which allow you to do some quite high-level programming for interfaces. You can do AJAX if you're dealing with XML, or JSON to exchange packets of information. We've got HTML5, which has more and more support and which allows you to make nice interfaces. And we've got all these VO protocols where you can query data. So I will mainly focus on the data and service discovery aspect in this session, which has to do with because that's where most of the semantic and goes in. We've got two choices, in my opinion. We can go for simplicity, or we can go to complexity. You can make a nice, simple portal, which is useful, or you can make a quite complex portal. You see all those widgets in the... well, it's not very customizable, but there are plenty of information in the Strasbourg Cathedral. In practice, I looked at a few existing portals. This is the VAO portal. You can maybe notice that the input here is quite simple. You can put in this box, in this search box, an object name or coordinates, and say what is the size of the area you consider around this sky location. And when you press submit, you will get a bunch of resources of results corresponding to a list of resources around this sky location. The input is very simple, and then you can filter the result with facets and so on. So it's a good example of a VO portal. If you go to ADS, it's slightly different. You still have a single text input box, but you can start to put some scripting in this box. You can categorize the input terms that you're putting in this. So you can say, I want to find papers which have cloud in the title and which are dealing with the thurs object, for example. And you've got additional constraints which you can put in your query. You can choose how you want to sort the result and so on. And you've got a possibility to log in. So you can categorize the input. You can choose somehow how the sorting will be done. You can log in. So once you're logged in, you get additional possibility. Well, maybe the portal can have some memory on your behavior and customize things for you. And again, on the result page, you've got this faceted search where you can restrict the range of the results. A slightly different portal is what was demonstrated by Andrew Connolly, I think it was 3 years ago at ADAS, 2 or 3 years ago. He made a portal, a demonstration called Ascot, and this is made of many individual widgets. Here you've got a name resolver. You put the name of an object, you get the coordinates. Then you can broadcast this coordinate or use them in conjunction with a widget which is writing a SQL query to some data set. And when you submit this, you can make a plot of the data in another widget. And so these widgets are talking to each other. And this is more data analysis portal than a simple data discovery portal. In fact, the data discovery is barely there because there are predefined buttons for the catalogs which you can query in this case. And then I'm coming to CDS resources. This is the current Vizier front page, or the Vizier full search. We've got a simple search where you've got 2 text boxes, but this is the complete Vizier interface. It's much more complex than the one I showed what I showed before. You can put here some text, whatever you want. This can be an author name, keywords, names of catalogs, a bib code, and the service will try to figure out what to make from this. Or you can say yourself what kind of constraint you want to put on the search. In fact, this single interface can do two different things. It can search for catalogs if you don't know them. So you can search, say, I want catalog with infrared photometry of pulsars. And you will try to find catalogs. Or you can directly, if you know the name of a catalog, put an object here, or search for an object across all the catalogs. So you've got quite different things you can do with the same interface. The point is that, well, it's complicated. I never show this to the students when I'm teaching databases or access to VO data, because it's too complex. So we came up a few years ago with the idea to have a single CDS portal where you can go and make a simple query, and this query will be broadcast to Simbad, Aladdin, Vizier, and we try to aggregate the results together. So currently, it's only limited to object name or position, just like the VAO portal. The benefit from that is that the web interface is very simple. You got a box, you put your target, it can be an object name, it can be a coordinates, and you press go, and then you get an aggregated result. You got Simbad results at the top. We made the selection of links. You know, we aggregate some information from Simbad, and then we give you some pointers. Find out more for this object in Simbad, or do you want to find all the bibliography for this object, or do you want to find similar object in Simbad, which is something that Simbad does not do. In that case, we take the object, look at papers and for this object, and look at other objects cited in those papers, and we make statistic on the fly, and so we say, oh, the papers which deal with this subject also deal quite often with these other objects. So there's some information that you can retrieve. This is a list of images which will cover this subject in Aladdin, and this is a list of catalogs. In fact, we've got two things for the Vizier results. We search first, are there some catalogs in Vizier which only deal with this object? Might be. These catalogs might not even contain sky coordinates. It can be XY coordinates, or just a list of numbered elements, or a strength of various atomic lines for this object. And the second one is we make a full positional search for this object in Vizier. So this is the current capabilities of the portal, and that's all. What we plan to do is to have some improvements. For example, we would like to be able to put additional inputs in the query, other than the simple object name or coordinates, and make some smart interpretation of this input, and then broadcast the query to the various services that we have, and possibly others, and still at the same time keep it simple. So that's not easy, and I try to summarize a few use cases we could ask to such a portal. What is the redshift of 3C273? Find information on globular clusters which are in M31, or around M31. What do you have about proper motion of brown dwarfs? Kind of make a SED for Vega. I just want the Veron catalog, or the Veron catalogs, because there are several versions. Quasars with redshift greater than 5. I want to cross-match the SDSS and 2MASS. What we can do. So I looked at existing portals. Most famous portal I think everyone is using quite often is Google. For the user, Google is simple. It's amazing that it remained that simple for so long. It's helping you by making suggestions. So in a way, you feel smart because as you type, you see suggestions coming. And if you're very lazy and it's fast enough, you can simply click on what is suggested and you don't have to type the full thing. And the suggestions as well as the results are nicely sorted. Sometimes when discussing with colleagues, they have scruples on sorting the output. Say, oh, who am I to sort the output for the user? I just give everything. This you cannot do when you have a data avalanche. When you have many data sets, you need somehow to find the most relevant ones. You cannot simply throw everything to the user. Imagine if Google throws all the web pages it has for one keyword. You would not use it. It's useless. But it means that server side, you need a heck of a lot of indexing. It needs to be very fast. It needs to allow for fuzzy searches. Find if you've made a typo. You want the system to tell you that you've made a typo and still find the right results and so on. And the second example I had in mind for requirements for improving the portal was Wolfram Alpha. Wolfram Alpha is smart. It's really smart. If you type M51 Redshift, it will say, oh, I'm assuming that M51 is an astronomical object. It's just good. It's what I want, and so it will interpret my input and just give me a result. That's nice, and it's on the user side. It's simple. It's just a single text box where you can put stuff. You can categorize it yourself. So there's a script where you can say this is a city, colon, and put the name of a city. But if you don't, you will try to figure out in various databases which are behind that maybe this string is a city name. And on the server side, there's a lot of interpretation of your inputs, and there are many, I should have put plurals here. There are many knowledge bases. They keep on harvesting data sets, knowledge bases, DBpedia and so on, and trying to annotate it with metadata so they can figure out what's in there and have many relations. So if you put two city names in Wolfram Alpha, it will give you the distance between the cities, the time it takes to fly from one to the other, and so on. So it's also about thinking about what you have in mind when you make a simple search.
Can I make a comment? So one of my complaints about Alpha is that it will sometimes give you complete garbage, and you can't tell. So it could have given you the redshift was 42, and you've got no way of telling. So there's no confidence interval or.
I think there's some.
If you put in
there are some sources here. For each result, it says where this is coming from, and you can go and figure out the origin of this.
So I don't know now. If you put in average height for Chinaman, it says 1.62 meters. Fine. You put in average height of anybody from anywhere in the world, usually the same answer. The last it may have changed. So it's that sort of thing. It's clearly picked up a number somewhere. It's actually misinterpreting. So one important thing is that it needs to use some measure of confidence.
Yeah, confidence and
whether that's like an error bar.
Yeah. Okay. So I will. I try to think. Okay, what are the simple things you need to build a smart portal? First, the portal needs to understand what you mean when you give it some input. For this, you need some kind of stemming. It's making sure that star and stars are interpreted in the same way. Lemmatization, where you deal with synonyms, so whether you type quasar or QSO will be interpreted the same. And then categorize the input, which is a problem of name entity recognition. And once you've done that, well, what can you do with it? What can you do with the query? So you must somehow match the annotated or entity recognized search string to some search templates in various contexts, which is what Wolfram Alpha is doing. And you must somehow maybe translate the query in each context. In the case of the various CDS services, they don't have the same metadata exactly for historical reasons, but we have to deal with it. So the first thing I really did was try to look at statistics and what do astronomers do when they search in Vizier. You got this text box in Vizier where you can type whatever you want. So I just took the logs of Vizier and look at the contents and what is used in there. If you do that, you can make some nice plots. So this is for a few, I don't know, tens of thousands of queries. This is the number of queries for each of the search term ranked by order. This is the most frequently used term, which happens to be the word "2mass." So it's been searched more than 1,000 times. Second most searched term, and so on. You can make this until you've got expressions which are searched only once. It's a very classical shape where it follows a power law. In fact, it follows two power laws. You've got one slope here and another one here. It's called a zip flow. You find this everywhere. Take a book, take every word of the book, compute how many times each word appears, rank them, plot the number versus the rank in log-log scale. You will find a power law. It's universal. Sorry?
This type of
you will find usually it's two. It depends. Sometimes there are one slope, sometimes there are two slopes. But it's something that is well known. But it means you can have many different searches, and a few searches will appear very often, and the trend is following a power law. Now I try to look at what is the average length of a search string. A number of characters, that how many characters do people type in the search box before with expectance to have a result. What is your guess on this? How many characters? 10, 15, 20?
8. Yeah, I guess so.
It's less. It's less. And it depends if you look at the total number of queries. It's 1, 2, 3, 4, 5. So 5 characters is the average, or it's most likely that people will type. If you look at the distinct search strings, then it goes to 6. So but most often it will be between 1. Okay, I don't know. 1 is not often, but between 3 and 10 characters. That's what people will type in the search box. It can be as large as, well, this is garbage, there. But a few tens of characters. So you must deal with that. People will not give you a lot of information, most often. And from the list of terms I extracted from the logs, I tried to categorize these search terms, and I made this very simple categorization. People will search in Vizier, well, for catalogs. They give the name of a catalog, 2mass. They can search for a mission, instrument. Sometimes it's the same word can be both. If I search for IRAS, well, IRAS is the name of a mission. It's also the name of the IRAS catalog. They can search for the name of a person. They can look for measurement, proper motion, redshift. They can look for object types. Spiral galaxies, quasars, object names, or positions, which are somehow, you can easily go from one object name to a position, or a data product. I want a spectra, I want something else. So I took my previous use cases and tried to categorize them given with these categories. And this is what you end up with. So these are already complex queries, given that people on average type 6 characters. But I can say, oh, I can search for proper motion of brown dwarfs or globular clusters in N31. So what do I do if I have an object type and an object? Is your question?
So is 5 or 6 characters what people are comfortable with entering, or is it more what is needed to uniquely identify or get results?
I think this is a bit biased. First, because the search box was quite small. It was maybe 20 characters, so you will not type a lot of text. And maybe this is sufficient to retrieve what they want. But if you want to make some more complex queries like this one, probably we'll type a bit more information. Or hopefully for me, you will give more information. Yeah.
The other thing is that you said that 2mass was the most searched term. That one has 5 characters.
Yeah, yeah. So building a smart portal, you have to. There's what the user wants. Maybe you know this cartoon, but there's what the user. I slightly adapted it. What the user wants, how he expresses it, when what is he typing in the search box. Then you've got what the portal will understand, and what the portal returns. You don't want to end with this. It's hopefully you want to be as close as the user desire in the output. So in order to interpret and tag the user inputs, the simple way is to say to the user, okay, please tag it for me. Use this syntax where you got this in ADS, you can type author this, or in Google you can say, I want result from this website, so I will put the site colon in front of it, and let the user do it. Or the hard way is, well, you let the user type whatever he wants and try to figure out what was meant. Okay. And so you can, to solve this problem, you can use vocabularies, but I will show just after that vocabularies are not enough. And what you really wish to do in order for the portal to feel smart or to be smart is you want to do it on the fly, ideally, and provide suggestions. As the user is typing, you want to be able to make suggestions. Say, oh, I know what you mean. I know what you mean, and I'm giving you hints on what I am able to understand. So I made some, these are first prototypes where you can say, for example, you can categorize your input with these categories. I define the target and the quantity redshift. You can give this as an input. The user can type it. You can provide ways to suggest it as you type. If you start typing quantity, what quantity start with an A? It can be absolute magnitude, abundance, age, and so on. You pick this from a vocabulary. In order to suggest, you need to make some queries, sort it, filter it. You don't want to provide hundreds of results. And this tagging and suggesting in general is, so it can be done with vocabularies and thesauri. But not only, you don't have thesauri for everything. If you take author names, where do you find a reference list of author names values? Well, you take ADS, you make complete statistics on everything, and you make statistics on author names, but then how do you sort? What are the most relevant authors in the output? That's a big problem. You can take, some on the next slide. It's more difficult for object names. Say we've got more than 20 million identifiers in Simbat. We can load all this in memory, it fits. But if you go to all the possible object names, they are specified by the Dictionary of Nomenclature, but we've got nearly 10 billion in Vizier. 10 billion identifiers for all the big catalogs, take 2mass, SDSS, and so on. And what you want to do ideally is, as you type in the search box, you will search for vocabularies, authors, and object names at the same time, trying to find what the user is typing. So there's a big issue of finding this and sorting. It's mandatory to sort things if you want to face the data avalanche. For this, you want to make use of some statistics. You can make statistics, for example, on the most queried catalogs, or present first the papers with the most citations. But I know people who are not happy with this. Oh, it's biased, you know, the winner will take all. If there's one catalog which is frequently queried, it will always come at the top. Yes, but that's life. That's what everyone is doing. If you don't do that, people will most likely that people won't be happy with what you present. They say, I'm looking for this one, it's the most used one, and it's not at the top. This is not logic. And it's not only the number or the usage statistics, it's the trend in the statistics. If you got, so you need somehow short-term statistics. What about a paper which is recent? It doesn't have yet a big number of references or citations, but it's got a high citation rate, so it's popular. So you want this one to move to the top, even if its total number of citations is low. So the last point I want to make before conclusion is you've got one query. Say you interpret it correctly. You search for quasars with redshift greater than 5. You've identified that quasar is an object type. Redshift is a measurement. You've got a numerical constraint on the measurement. And then you need to broadcast this query to different services. They will talk different languages. They will have different metadata. So you need, in Simbad, quasars are called QSO. Redshift is called redshift. In Vizier, you have to look for astronomy keywords and QSO with the S, and you find the redshift with the UCD. You need mappings between all this. And this is probably the hardest part, the hardest in the work of making these smart things. So I just summarized a few ideas I presented to you. I want to build a smart portal which will be able to do some data service and new features discovery. It's important. We released a cross-match service. It's able to cross-match big catalogs and so on. There are still people who will query Simbad with a list of 20,000 objects one by one. They make 20,000 queries. They don't know that there's a service which can do this in seconds. They will overload your server and so on with thousands of queries. So if people say kind of object by list and this, you want to say, hey, there's a service which is able to interpret your query. Building a smart portal is kind of extreme text mining. You've got very short input strings, and it makes things more difficult than, or it's another challenge than mining the full ADS corpus. You can learn from your logs. Look at what people are searching, and you will probably serve them better. There's no such thing as too many metadata. If you want to interpret queries in various contexts, you will always find a point where, why don't we have this piece of metadata in the database? Oh yes, you can add it. It will take days and days of work. So think about metadata early. Sorting and suggesting is important. You can learn from the actual usage of the portal. If users are registered, you can even customize the output, remember what they've been searching for, and provide it in the output. Things are changing. It was said earlier, the vocabularies can change. There can be new data. There can be obsoleted data sets or services. You need to take this into account to have a dynamic answer. And the last point is, do not underestimate the carbon-based intelligence. You will never be able to build a portal which is smarter than the user, or I don't think so. But you must have confidence in the user. He will be able somehow to rephrase its query to find what he wants. So don't try to envision all the possible cases. Try to be smart enough with the portal, and the user will be smart also with you. Thank you.
We've probably got time for one question. So,
the visual that your portal generates, what would be the solution when it is about multidimensional data? What visual do you?
I'm not planning to do. Sorry.
Can you repeat the question?
Yeah, the question is what we plan to do with when the result is multidimensional data. At this point, the portal will not be about visualizing the data and so on, but mostly locating or interpreting the input and redirecting the user to specific links. If we can provide the numerical answer and do it, it's good. If you ask for a redshift, and do it. But if the user asks for globular clusters in M31, you will say, oh, I can search for a catalog containing this kind of object type, such as globular cluster, and make a search in the area of M31, and tell the user, oh, this is the kind of query you can construct. Then you can customize it. Or in Simbad, you can search for filter on object type, stored in Simbad. Same thing, look around M31, customize the output with a search radius, and so on. So it will be more like providing the user with the list of directions in which to get different results than trying to integrate and visualize everything in the same page. This is for later, much later probably.
Okay, we will take 20-minute break, if we may, and then we'll reconvene at 3:07.